I'd like to start in chapter 10, that's on inductance and transformers. The book does a slightly different, it does the inductance first and then a transformer, but since we've already talked the magnetic field, I think it makes more sense to look at the transformers first, and then we'll look at the inductances and the circuits involving inductances in chapter 11. If you look at just a regular transformer, you have your primary and the secondary winding. Of course, we're going to talk about AC only, because if you're applying a DC voltage here, it turns out the voltage induced by Faraday's law, it has to be a varying magnetic field. If it's a constant magnetic field, you produce a magnetic field, but the voltage would be zero. So you definitely need to have an AC signal. Now, if the current is going in that direction, you wrap around the right hand rule, use the right hand rules, you wrap the right fingers in the direction of the current flow. Your thumb will give you the direction of the magnetic flux. So in the primary, the first winding is called the primary, V sub P, that's the voltage across the primary, the number of turns in the primary, and then the number of turns in the secondary, and the voltage, VFS, is the secondary voltage. The magnetic flux that is generated also via sine wave. If you're putting a pure sine wave in here, if I look at the magnetic flux phi sub m, it's a mutual magnetic flux, that the flux that actually be generated, part of the magnetic flux that is generated from the primary will go into the secondary. That's how the voltages get transferred. The energy gets transferred through that magnetic field. Phi sub m would be some peak value. Sine of omega t is a pure sine wave. But there's some flux leakage. Not all the flux is generated in the primary. It's going to go to the secondary. And that's called phi 1,1 partially. And that's what is called the mutual flux. Phi sub m will be pure sine wave, and that's called a leakage flux. Because of this leakage flux, we're going to see later, you produce an inductance in the coil. Will have some kind of reactance to the voltage itself. The way the inductance works here, this V sub P is very close for V sub T. Otherwise, when there is nothing hooked up to the secondary of the transformer, there is no current flow in the secondary. So the primary current ideally should be zero. But you have less than 3 or 4% of the rated current is going to flow just to set up the magnetic field. That's the energy you have to put in to set up the magnetic field, so you'll be able to transfer that energy. So this V sub P here is very close to V sub T if there's nothing hooked up to it. When there's a load hooked up to the secondary of your transformer that generate the flux in opposite direction, it reduces the flux and then reduces the voltage, and then you have a higher current. So a transformer is just like a motor, actually regulates its own voltage and current when you have a load hooked up to it. It's just like at a motor, if you put a load on a motor, then the speed will go down, and then you pick up the torque to rotate whatever it is hooked up to the motor. We'll look at that in details later, how the voltage is actually generated using Faraday's law. So the flux phi 1,1 is called a leakage flux. If you have an iron core, they use this symbol, double bar in the middle. If it's air, there's nothing in it. As we talked about this before, you don't really want to do that, because if it's air, the reluctance is extremely large, and therefore you have a very weak magnetic field. So either they use ferrite materials, which is a dotted line, or they use a iron core with a solid line. That's the symbols they use for the transformers. Now, the application of the transformer is either you can, as a setup, step-up transformer. When N sub S is greater than N sub P, then that means the voltage VFS is greater than V sub P. The transformer will be a step-up transformer. So V sub S, the secondary voltage will be greater than primary voltage, or a step down the transformer where V sub S is smaller than V sub P. We're going to look at the application of those where you're doing a step up and then the step down transformers. You can also use them in oscillation transformers. If you look at your power supply that is hooked, your 120 volts coming, 110 volts coming out of the outlet, you need to reduce that voltage down to 24 volts, and then to hook up to the power supply, and then it gets rectified so you have a DC voltage coming out. What it really does here, not only is step down the voltage, it also provide on oscillations from AC to go to the DC. So the AC is grounded, but you want to oscillate the ground for DC, and you can do that with what's called an oscillation transformer, because the transformers are magnetically coupled but electrically oscillated. There's no electrical connections. Unless it's auto transformer, that's different applications. You don't want to use auto transformers and oscillation transformers, because with auto transformer is also called variac. The primary and the secondary are on the same core, therefore they are electrically connected. There's advantage and disadvantage with this. The advantage is it turns out that you can transfer higher rating, power rating with auto transformer from the primary to the secondary. The disadvantage is if the secondary will break, then you have a very high voltage cross your load, and it could easily damage the voltage. But here, if the wire breaks in the secondary, nothing is going to happen to the load. So that's the disadvantage with with the variac and auto transformers. You can easily slide it. It's just like a variable resistor, like a voltage divider that we did. It does operate exactly the same way. You can go from 0 to 120 volts, and you have a knob like a tab. You can adjust to whatever the output voltage you want on your secondary. You can also use them as a three-phase transformers. We talked about this before. The power companies, they use three phases. It's more cost-effective to transfer the power in three-phase or a long distance than it is to with a single phase. And there are 4 or 5 advantages with a three-phase versus a single phase that we're not going to get into, but those of you who be taking a power system, you definitely get into that. Here's the generator, the power generator. We can generate from about 13.8 kilovolts to about 24 kilovolts. And that voltage is step up and jacked up to about 138,000 to 765,000 volts. And you do that with a three-phase transformers. What they do delta to Y connection, which we're going to discuss in a minute. If you jack up the voltage so high, the current is going to go down in the secondary, and then you have I square all losses in the transmission line, which will be very small, because the power company, they're paying for transmission losses. They only charge the consumers at their location, so whatever they lost on the transmission line is really a loss for the power companies. Now, if I look at just a simple transformer, you get the primary voltage, secondary voltage. They use a double line here. It gives you the number of turns on the primary and the number of turns of the secondary. The ratio of the voltage, V sub P or V of S, is directly proportional to the number of turns on the primary over the number of turns on the secondary. So if I solve for the primary voltage, multiply both sides of this equation by V of S. If N sub P is greater than N of S, then V sub P would be greater than V of S. And that's step-down transformer. If it's exact opposite, if N of S is greater than N sub P, then V sub S will be greater than V sub P, and that would be a step-up transformer. So the secondary voltage would be greater than the primary voltage. Now, ideally, what you're really doing is the power that you're putting in, V sub P times I sub P, has to be equal to the power they're getting. It's a conservation of energy, assuming there's no losses in transformer. Again, that would be the ideal case. So ideally, the power that you're putting in, P input, has to be equal to P output. Well, I'm sure you all remember that the power is V sub P times I sub P. Just looking at instantaneous power. Be V of S times I of S. Now from here you can see that I sub P or I of S has to be equal to V of S times V sub P. You can write this equation with a ratio. Or you can say I sub P or I of S is equal to N of S or N sub P. Compare equation 1 and 2. Here you can see if V sub P is greater than V of S, if N sub P is greater than N of S, then what happened to I sub P? I sub P then would be equal to, if N sub P is greater than N of S, then I sub P will go down. So if you jack up the voltage, the current will go down, and vice versa. And that's because of conservation of energy. So if N of S is greater than N sub P, this would V of S then would be equal to greater V sub P, and I of S would be less than I sub P. And that's exactly what they do with the power transformers, three-phase. What they take 3 single-phase transformers. You can have them three-phase, building a three-phase on one core, all the 3 windings, in form of a delta, or you can have 3 single-phase transformers and hook them up as a three-phase. Here's transformer 1, primary, secondary. They're 3 identicals. They also called what is called a dot convention, and that's the way the winding has been done. So the manufacturer, they always put a dot on the transformers, and when you do delta to Y, this is the schematics diagram, but if you look at it symbolically, here's phase 1, phase 2, and phase 3. On your primary, they take 3 delta transformers, they hook them up as a delta, they hook undotted terminals to dotted terminals, undotted to dotted, and undotted to dotted, and then those dotted terminals will go to the line. So you put everything inside a box, that'd be a three-phase transformer, but it's a delta Y connection. This is line L1, L2, and L3 is coming in, and then it will go out. And a Y connection, you tie undotted terminals together, and then dotted terminals will go to the line. And those are L1, L2, and L3 will be L1, L2, and L3 here. So this is how they show delta to Y connections for 3 single-phase transformer to generate a three-phase. And this is the schematics. What that really does, this is called delta Y connections. They use delta Y connection to step out the voltage, as we talked about it earlier, about 138 to 765 kilowatts. There's the advantage of that. There's a square root. We're not going to get into a three-phase circuit analysis at this point, but there are advantages. When you do that, you save square root of 3 for the winding, and then when it gets to the distribution area or residential area, they drop the voltage down and they use Y delta connections. And there's a cost effective, the reason why you do delta to Y, to jack up the voltage, and then when you want to step down the voltage when it gets to the distribution or residential area, then they use Y delta connections. And there's a factor of square root of 3 saving in the windings when you do that. Now the transformer, it looks almost identical. Sometimes they call them mechanical transformers, mechanical gears. It works exactly on the same principles. If you take a set of gear train, like a bicycle, here applying a torque, and then there's a current or the angular displacement. That's your primary, let's say, is 200. The number of T is equal to 200, and the secondary, let's say, is 100. So it's 2-to-1 ratio. So if the primary does 1 revolution, the secondary will do 2 revolutions. So just like the speed is going to go up. So the torque on the primary or the torque on the secondary would be equal to the number of teeth on the primary or the number of teeth in the secondary. But if you look at mechanical power, it's just very similar again, just like the voltage. So the voltage does act like a torque in a gear train that it is with the voltage in transformers, electrical transformers. But ideally, the power that you're putting in in the primary is equal to the power you're putting in, you're getting out in the secondary. But what is a mechanical power? Well, electrical power is V sub P times I sub P. When you do mechanical power, it's actually equal to torques times the speed. Or we talked about this, actually equal to omega times the torque, the mechanical power is equal to torque times omega sub m, which is angular speed. So if you gear down, when the speed goes up, the torque will goes down, and vice versa. When the speed is lower, when you go to lower gear, then the torque will go up, but the speed will go down. So the speed acts like a current in a regular transformer, and torque acts like a voltage in a regular transformer. And that's ideal. So you can say this is the torque, and this is the speed. On the secondary, you have the angular speed, and then you have your torque on the secondary. So it's exactly, in ideal case, it acts like a mechanical transformer with a set of gear trains. But nothing is ideal. If you look at a non-ideal case, there's 3 losses associated with a transformer. And again, in the power applications, the efficiency is very important, so you want to make sure you make it very cost effective. So you want to keep those losses down as much as possible, so you have to close to 100% efficiency. But with the power transformer, you got about 98% or so efficiency, because there's some losses which we're going to discuss. One is called the copper loss. The copper loss is that's the I square R loss. That's the power that is dissipated in the winding in the form of a heat. So you have the primary have a winding. Of course, the winding will have a resistance. So it would be I sub P squared times R sub P. That's the current in the primary squared times the resistance of the winding of the primary. And the same thing with the secondary. Secondary, you have a winding, it has a resistance R of S, and then the current I of S, depending whether it's a step-up or step-down transformer. So, excuse me, R sub P and R of S are winding resistances of the primary and the secondary winding. There's also another loss called eddy current loss. Here you have your transformer, the core, and which is inside the magnetic field, and every time you have a conductor inside the magnetic field, you get a varying magnetic field will definitely generate a voltage according to the Faraday's law. So if you have the voltage across the iron core, the core itself has a resistance, and if you look at the cross-sectional area of the ferromagnetic or your core, and it has a resistance that is inside the voltage, then you definitely have a very small current flow. And that's called the eddy current, after the guy named Eddy for the first time when actually discovered and measured this current. Then what is called a core loss. Again, we have copper loss. That's the power dissipated in terms of heat in the winding. And then eddy current loss. And then we also talk about hysteresis loss before. And they referred that to as a core loss. Core loss is the eddy current loss plus the hysteresis loss. In order to minimize the eddy currents, if you look at any transformers, in order to reduce this current, then they use laminated. They use laminations. What that really does is a thin sheet of ferromagnetic materials. They put together an oscillator with some kind of insulators. What that really does is put a very high resistance on the path of the voltage. So if you have a high resistance, then you have a very small current flow. So that's one way to minimize the eddy current losses. And we talked about a hysteresis. We said if you take a simple core and wrap around a piece of wire, and then try to adjust the current, you set up the magnetic field. And if you want to reduce it and bring it down back to zero, you have this residual magnetization. And to bring it down to zero, then you have to apply a negative current. And again, we talked about this in detail. It will go back to original. This area right here, that really gives you what is called the hysteresis losses. What they do to minimize the hysteresis losses, they add 2 to 3% silicon impurity to the iron core. What that really does is it will reduces the hysteresis losses. It takes less energy to study the magnetic field. Once you have calculated the losses, then you can calculate what the efficiency is. The efficiency then would be equal to the power out divided by power in. And power out is voltage in the primary, the voltage in the secondary times the current in the secondary. But you can say the power input is equal to power output plus the losses, core losses, which was eddy current and hysteresis. And then you have a copper losses, which is I square R losses, and that's both from the primary, so you really have two terms in your I square R of A, and then plus I square in the secondary times the resistance to the winding. Here, that's the rating of the transformer. There's not much you can do here. You cannot adjust that. But you try to minimize these two losses to have a better efficiency of a transformer. To calculate the efficiency, they come up with a nonlinear model. This is the secondary. You have the winding. You got the resistance of the secondary. And then you have inductance, which we're going to discuss how this inductance was actually carried, as we talked earlier. That's due to flux leakage, Phi11, that does not go to the secondary. And what that happens, it's really called the leakage inductance. The same thing here. Get a resistance to the primary, the inductance of the primary winding, and then this is where the losses comes in. This is called, that's not the eddy current law, that's really excitation current. If there's nothing hooked up to the transformer, so there's no current flowing in here, and you look at the relationship with the need that I primary over the I secondary is equal to N of secondary divided by N of the primary. So if there's no current flowing here, when the transformer is, there's no load hooked up to the secondary transformer, so basically there's no current be flowing in this part of the circuit as well. But if you put an ammeter here, you measure a very small current. Well, that current is called excitation current, which is going to remodel with this branch right here, which I said is about 3 to 5% of the rated current of your transformer. Now, this excitation current will have two branches. One, we put inductance in here to count for hysteresis losses, which we need to calculate this model. And there are two tests done called a short circuit and open circuit test, because you cannot really measure this, but you can indirectly determine what this inductance value is. The same thing with the resistance of the core. This will take care of the eddy current losses. So this magnetization branch here, it really takes care of the losses that we can use as a model, be able to calculate the eddy current losses, the hysteresis losses, and then, but you can always calculate what the core losses is. The copper loss, which is IP squared times R sub P, and then I of S squared times R of S. So in this case, for this non-ideal model, R sub P is the same thing, primary winding resistance, R of S is secondary winding resistance. L sub P is inductance, that's the leakage inductance on the primary, and R sub C is the core resistance, that's for the eddy current loss. And L sub M called the magnetization inductance, that's to take care of the hysteresis losses. Once you have those, then you should be able to calculate the actual efficiency. And as I said, there are techniques available or tests they call open circuit and short circuit tests. And with the small measurements, you put an ammeter here, you put a voltmeter here, and you put a wattmeter across the magnetization branch. You make three measurements, one with the primary open, and one's with the primary, with the secondary open, and one's with the secondary short circuited. And then when you take that data, you should be able to come up with R sub C and L of M. Then you have a complete model for nonlinear transformers, and then you can calculate all the losses to come out with the efficiency of the transformer. which they try to minimize it as much as possible in the power applications. Now there's a thing called a quality factor, or Q, of inductance. Ideally, if I have a simple inductance, this is what it looks like. That means the winding resistance is equal to 0. All I have to do is, if you have a current flowing in here, then you generate a magnetic flux, and that magnetic flux will generate an inductance value. But that's not the case. The resistance of the winding, it has to be taken into the consideration because that's part of the coil. So we're going to model this as R of the winding, and then this is the inductance of the winding itself. Now if you put an AC voltage in here and look at the current and put a wattmeter in here, you can measure the power that is dissipated inside a coil, and that wattmeter reads what is called the true power or the real power. Okay. Again, if you have ideal inductance, will not dissipate any energy. All it does is store that energy inside the magnetic field. But in an ideal case, the practical, you do have some losses, and that losses would be in the form of heat losses in the winding of your transformer or the coil. Now, the wattmeters, again, just like the meter in the residential area, when they read the power, it reads whatever that value is called the real power, or the true power, or the actual power. It reads the average value of instantaneous power. And we'll talk about this in a minute. There are three powers that we're going to look at. One is what is called apparent power, which is voltage times the current. And that called P sub A, that what it appears to be in AC. You know, with DC, calculation is very easy, as we've done it already. The power in DC is just simply equal to the voltage times the current. Well, it's not so easy in AC applications because there's the inductance value or the capacitor value is going to come into the picture in terms of the actual real power or the true power. So whatever this wattmeter is reading is actually the power that is dissipated inside the winding resistance of the of your load, in this case your inductance. And that gives the real power. So if I look at here, you got a voltage, you got a current, here's the resistance of the winding, and this is the inductance itself, L. Well, it turns out that the inductance reacts against any current, and that reactance is a function of the frequency, which is equal to 2 pi f times L, or just simply omega L. So which means is if you have if a DC signal is coming in here, then the DC signal frequency is equal to 0. So inductance reactance X of L would be equal to 0. Okay. But whatever the wattmeter is reading is really a power that is dissipated inside the winding. So the power, which is called the real power, that's the wattmeter reading, is equal to I squared times RW, and then this I is the RMS value, it's not a peak value. There's another power, it's called Q, that's the reactive power. That would be equal to I squared times X of L. This is not a power that is dissipated. This is called the shuttle power. This is the power, there's not much you can do about it, that actually bounces back. On positive cycles, it goes into the coil. In a negative cycle, it will bounce back, but it will not dissipating it. And because of that, they call that a shuttle power. We can look at what is called a power triangle. Here's the real power. This is what the wattmeter is reading. This Q is the reactive power, is a 90 degrees phase shift. And if I look at this triangle, then if I look at this here, that's called P sub A, that's your apparent power, which is equal to voltage times the current. And this angle is theta. Now they look at the quality factor, which is Q. The quality factor of a coil is equal to whatever the reactive power is divided by the real power. Well, we already calculated what the reactive power is. Reactive power is equal to I squared times the reactance part of the coil, X sub L. Again, X sub L, it does have, if you calculate 2 pi FL, it's united in ohms also. So the real power is I squared times RW. I squared will cancel out. You're left with X sub L divided by R sub omega. R sub W, which is the resistance of the winding. So this is the reactance of the coil, and RW is the resistance of the winding. That's actual resistance that you put on a meter and then measure it. Now, if this quality factor is anywhere between 0 and 20, is referred to as a low Q. If it's greater than 20, it's called a high Q. Or I could say that Q is equal, if I replace a reactance with 2 pi F times L divided by R sub W, the resistance of the winding. When the signal is coming in, the wave with a certain wavelength, and here's your antenna, then the energy gets picked up by the antenna. It will develop a very small voltage, around 10 millivolts or so, and with the resistance or Thevenin, which is the resistance of the antenna, you can model that with a Thevenin. So every time the signal is coming in, you have a very small voltage develop, and you can model it with a Thevenin. And you have a what's called a tank circuit, which got a capacitance and an inductance. You can adjust the capacitance C if you're tuning, if you got a single transistor radio and you want to tune it to pick up the frequency is coming in. This is what happens with a low Q and high Q. If it's a high Q, this circuit acts like a filter. When it's high Q, it's extremely sharp, and you're just going to pick up that frequency is coming in. If it's a low Q, it's flat on both sides, it's not as sharp, then you pick up all kind of noises, all kind of frequencies. And so if you have a tank circuit, you definitely want to have a high Q such that you don't pick up any noise or about the frequencies that are coming in as that you want it to pick up. Some of the problems that we have with inductance, we're going to talk about them in the homework problems. So we're going to look at a set of problems in chapter 10, 6, 9, 12, 15, 16, 20, 21, 26, 31, 34, 41, 49, and 51. Let's look at the first one, number 6. So on page 320, it says calculate the value of the air core inductance shown in figure 1042b. 1040b, they have a coil with a number of turns equal to 80. The length of the coil is 4.8 centimeters. The diameter is 0.3 centimeters. And it says mu sub 0 is equal to 4 pi times 10 to the minus 7, which is the standard value for the constant mu sub 0. Now the inductance is equal to mu sub r mu sub 0 times n squared times A divided by L. Now if it's air, it doesn't tell you the mu sub r. So if its mu sub r is not given, they're assuming this is not solid, it's hollow. Then mu sub r is equal to 1, mu sub 0 is equal to 4 pi times 10 to the minus 6. The number of turns is 80. Now, A is a cross-sectional area. It has to be in meters squared. So the cross-sectional, the area, you take 4 over pi times the diameter quantity squared, but you must convert the diameter into the meters. So 0.3 centimeters is 0.3 times 10 to the minus 2 meters, and you square that. And then the length has to be in meter also, 4.8 times 10 to the minus 2 to convert it from centimeters to meters. If you calculate that, it comes out to be 1.185 times 10 to the minus 6 Henry, or just 1.185 microhenry. And number 9, it says the coil in figure 1044A on the same page 320 has the value of K is equal to 0. Calculate the total inductance in the circuit. Now, the inductance, when they're connected in series, they act exactly like a resistors are connected in series. But there's a thing called a mutual inductance, because some of the flux that is generated in one coil, it might leak the second coil. And when that's the case, what's called a coupling coefficient, then the reactance or the inductance will be different. But in this case, it says K is equal to 0. That means the coupling coefficient is equal to 0. Then the total inductance just simply be equal to the sum of the three. So the inductances in series, they act exactly like resistance. If they're connected in parallel, then it acts like a resistance in parallel. The capacitance is exactly opposite. We're going to see later, if you got two capacitors connected in series, they act like a resistance connected in parallel. So the total just simply add 3 100 millihenry, 3.3, but 470 micro is 0.47 millihenry. So you need to convert that to millihenry so you can add them all up. So that one is pretty straightforward. And number 12, it says the inductance shown in figure 1045B are connected in a series opposing fashion, assuming that the coefficient of coupling between the two are 0.33, calculate the total inductance in the circuit. So here you have two inductance. The winding is done such that the magnetic flux are opposing each other, and the coupling coefficient is equal to 0.33. So the mutual inductance between the two is always equal to K times square root of L1 times L2. So from here you can calculate the mutual inductance. L7 would be 0.33 times the square root of L1 is given to be 4.7 millihenry, and L2 is 2.2 millihenry. So those are given in the problem. So the mutual inductance then would be equal to 1.061 millihenry. Now, if you got two conductances very close by, if the mutual inductance are either opposing or they be in additive mode, then the total inductance is L1 plus L2 either be plus 2Lm or minus 2Lm. So if they're opposing each other, like in this case, then it will be minus 2L, minus 2L of M. But if they're additive mode, then would be plus 2L of M. So that's the model for two inductances if there's some mutual inductance between the two. So if you're either opposing or they're not. So all you have to do is determine what the coupling coefficient. This coupling coefficient K determines what percentage of one flux is going to the second coil. That means that 33% of the flux is generated in one actually going to the second coil and vice versa. So that gives you a 4.78 millihenry. So those are the few problems that are straightforward calculating the inductances. Let's go on, move on to number 26. It says calculate the Q of the inductance shown in figure 1051B. 1051B, they got some AC voltage with a frequency of 10 kilohertz, and then they have inductance of 22 millihenry. The winding resistance is 2.4 ohms. That's actual resistance of the winding. They want you to calculate a quality factor. Well, we saw the quality factor is X of L divided by RW. So if you have the inductance value, you have the frequency, you should be able to calculate what the reactance is of the inductance. Again, the inductance, just like capacitor, capacitor will act against any voltage cross it. The inductance does the exact opposite. The inductance will react against any change in the current, and that reactance is a function of a frequency, which is 2 pi f times L. If it's 0, if it's DC, the inductance acts like a short circuit. If it's a very high frequency, it's going to act like an open circuit. And the capacitor does the exact opposite. So X of L would be 2 pi f times L. 2 pi frequency is 10 kilohertz, which is 10 times 10 to the 3. And the inductance, you must convert it to the Henry, which is 22 times 10 to the minus 3 Henry. If you calculate that, it gives you X of L is 440 times pi, and pi is 3.1415. It gives you 1382.3 ohms. And that's a very high quality factor, because if you take X of L divided by 2.4, it gives you 575.6, and it's definitely a high Q. Let's look at problem 49. It says, determine the frequency of operation that will provide a current of 100 milliamps to the circuit shown in figure 1059. So here you have, see 1059, you're putting a 10 volt source, AC source. The frequency is not given. You want to determine the frequency. It's 1 millihenry inductance, and then 200 microhenry. But the coupling coefficient is equal to 0, so that means they're completely oscillated. None of the flux is generated in coil 1 is going to the coil 2, and vice versa. There's no interaction there. But we want to determine how to adjust this frequency such that you generate a current of 100 milliamps. If I look at the total reactance, is always equal to V of S divided by the current I of S. Excuse me. V of S is given to be 10 volts. I of S is 100 milliamps. Convert that to amp. So X of LT then will be 10 divided by 0.1, which is 100 ohms. So in order to have a current of 100 milliamps, then you definitely need the reactance of 100 ohms, so the frequency has to be adjusted such that the total reactance is equal to 100 ohms. Now the two inductors are connected in series, so total inductance would be L1 plus L2, 1 millihenry plus 200 micro. 200 micro is 0.2, so you need to convert that. So that gives you L total of 1.2 millihenry. Now X of LT is equal to 2 pi f times L of t. And we got X of L of t, which we calculate. We got L of t, so we can, from here can calculate what the frequency is. So the 100 is equal to 2 pi f. L of t is 1.2. Milli is 10 to the minus 3. So make sure you take care of the units. And if you calculate that, it comes out to be 1.26 megahertz frequency. As you adjust the frequency, what happens to the inductance value? The inductance value is going to go up because the inductance reactance is a function of the frequency, is directly proportional to the frequency. And when you do that, you have a constant voltage source here, 10 volts RMS, then the current is going to go down as you increase the frequency. If it's extremely high frequency, then inductance is going to act like an open circuit, and the current is equal to 0. At the low frequency, or DC, the inductance is going to act like a short circuit, and you have a very high current. So as you increase the frequency, the current is going to go down drastically until you get a high frequency. It acts like an open circuit. Next problem is number 51. It says the operating frequency of the circuit shown in figure 1061 is a variable. So you have a variable, you got a frequency generator, you can vary the frequency. It's called a generator, function generator. Determine the value of IRMS and F when the inductor has a value of the quality factor of 25. They give you the inductance value, 1 millihenry. The resistance of the winding is 6 ohms. And they want you to calculate the frequency and the RMS value of the current if the quality factor is equal to 25. Well, the quality factor is 25. The resistance of the winding is equal to 6, so from here you can calculate X of L. So 25 is equal to X of L divided by 6. Therefore, X of L is equal to 6 times 25, which is 150. Now the current would be equal to V of S divided by the total reactance. In this case, it's 150. And also the frequency, X of L. Once we have X of L, you get T pi F times F of L. L is given. X of L we calculated. You can calculate what the frequency is. So plug that in. Frequency then would be equal to 150 divided by 2 pi times 10 to the minus 3. So it goes up, it becomes 10 to the plus 3. And if you calculate it, it gives you 23.87 kilohertz. And IRMS is approximately is equal to V of S divided by X of L. So that's 9 volts given in the problem. And X of L we calculated to be equal to 150. But that's the approximation. It gives you 0.06 amp, and that's your RMS is 60 milliamps. But in reality, this impedance, we're going to see later on in chapter 11, to calculate a current is really a function of inductance reactance as well as the winding of the resistance winding of the coil, because that will affect resistance, which actually lower the current value. Now we're going to see later, the next chapter, the impedance for the simple RL circuit is equal to square root of X of L squared plus the resistance of the winding is square root of it. If you calculate that, the actual calculation would be equal to 9 volts divided by this quantity right here. So if you look at 36, it's very small compared to 22,500. That's the resistance. Now, it's 150. It's very large compared to 6 ohms. So you're really ignoring 6 ohm when you're doing this approximation here, calculating the RMS value of the current. You're assuming R of the winding is equal to 0. But to be exact, you must calculate the total impedance, which is the reactance squared plus the resistance squared, square root of it. And that's called impedance, which we're going to discuss more in details in the next chapter. Every time you have an AC circuit, the inductance will have a voltage cross it, and the resistance will have a voltage cross it, but they're not in phase. They're 190 degrees out of phase. And that's where it gets a little bit complex when you're dealing with AC circuit. With the DC, it was just was a clear cut. You just do the calculations. But with AC, you cannot combine the inductance reactance with the resistance. They're out of phase, and then that's why they do phasor calculation, which we'll discuss in the next chapter. All right, we'll stop here. Please take a look at those problems. If you have any questions, email me, and I'll be happy to go over. Okay.